All right, 2.6, pre-calc, brace for impact, dealing with properties of rational functions. I need you to do the impossible on this one. This has a lot to it, even though we have three objectives here. Finding the domain of a rational function. This will become really heavily revolving around the denominator of a fraction. We'll see what vertical asymptotes are. So pretty much we've graphed out some of these, but we've seen weird phenomenons where sometimes the graph will dodge a certain line. It looks as if it's going to go very close, but not quite there. So we'll see exactly how we can get this based off of the function. We'll also see horizontal asymptotes, not so much oblique, but horizontal asymptotes pretty much do the same kind of thing. Actually, this was vertical. Right, so this line right here is the horizontal asymptote. Vertical asymptote would be the vertical line that it looks as if the lines are going to hit, but they don't necessarily hit. So I'll denote the vertical with pink. So what are these? These are the vertical asymptotes, which kind of makes sense. Vertical is going to retain a type of equation like x equals some number. Horizontal asymptotes will say something like y equals some number. This is really important because these do have characteristics of a line. So eventually for the next part, when we get to it, you'll have to denote what x equals or y equals. Domain. Main thing here is that we don't want a fraction with 0 and then some number up top. We don't want it. So our goal here is to try and pinpoint exactly what number this would have to be when plugged in to make this 0. The process for this is pretty easy. We just take our denominator, which in this case is x plus 2, and we know that this can't be equal to 0. So when we solve this, just get rid of 2 on both sides. This says that x cannot be equal to negative 2. So what does this mean? If we use interval notation, we want everything from negative infinity up to negative 2, but we want to skip negative 2 in reality, but then we want to keep it going to negative infinity. That's what this means. If you're not convinced, we can check the graph. The graph looks like this. For 2 over x dividing with x plus 2, we see that this looks very, very close, as if it's going to eventually hit negative 2, but it doesn't quite. Reason this is again because of the denominator. It's very constricting on that. So that's why we want to say for our domain, collectively can't be equal to negative 2. For this is x squared minus 9. You could isolate x and do that, or you could denote it as factoring x plus 3, x minus 3, eventually saying that x cannot be equal to positive or negative 3. That's okay. Interval notation will look something like this, going from negative 3 to 3 in union with 3 to infinity. If you're not convinced, it would look something like this. We see some weirdness when x tries to approach 3, when x tries to approach 3 but never does quite get there. And also for negative 3, we see that same kind of thing. For this, x squared plus 1, well, think. Can any number when squared equal negative 1? Like if you try to solve this, are you going to get some number? You won't get a real number. So in this case, we say it's actually all real. The reason this is because we can't necessarily solve for x. We can't take the square root of a negative number unless we're taking complex roots, but in this case, that's not happening. So that takes us to here. X squared minus 4x minus 5. You know, same kind of song and dance, say it can't be equal to 0. This is a trinomial, so channel that factoring from way back when. Your product's negative 5, your sum's negative 4. Factors here are negative 5 and positive 1. So you can rewrite this as x minus 5, x plus 1. This can't be equal to 0. Eventually, you'll want to say that x cannot be equal to positive 5 or negative 1. And this seems kind of bizarre as to why this happens, because it's a trinomial, but trust me, that's the case. As you see from the previous problem, yeah, there's no x value that's excluded. For problem D, you see that 4 and 5 are the weirdness. Or sorry, positive 5 and negative 1 are the weirdness. So as you see here, they're kind of conflicting over that point of x equals negative 1 and x equals 5. As far as when we graph these out, what's going to be helpful here is going to really be the explanation from the textbook. Although it's kind of dry, this really helps us out. So first with horizontal asymptote. We first locate horizontal asymptotes according to the following. And this all depends on the first leading term for the polynomial in the numerator. What this says is that if the exponent in the numerator is less than the exponent in the denominator, the x-axis, or y equals 0, is the horizontal asymptote. So let's make a note of that real quick. On here, if the top is less than the bottom, so if top is less than the bottom, then the horizontal asymptote is y equals 0. What else can we get away from this? If the exponents are equal, the line y equals that fraction or quotient between them is the horizontal asymptote. So let's also write that in. So we know that if the top's less than the bottom, horizontal asymptote's y equals that number. If the top is equal to the bottom, we take the coefficients, which let's say is like a over b, and that would be y equals that. On the flip side, what do we have? If n is greater than m, the graph has no horizontal asymptote. So we can also denote if top is greater, there's none, no horizontal asymptote. I abbreviate HA. So we have a little bit of work to do. Let's start first with horizontal asymptotes for these. So if we look closely for the first one, we see that we're dealing with x terms of 1 and 1. So what this means, they're equal. Top and bottom are equal. We can just take our coefficients of the top, which is 4, over negative 1. This should be y. So we have a horizontal asymptote when y equals negative 4. For the next one, we have the top exponent greater than that number. So since this happens, there's actually no horizontal asymptote, as mentioned here. So 3, the top is greater than the bottom, so there's none. For the next one, same song and dance, x to the 4th, greater power than 2. So there's no horizontal asymptote. That being said, when we get to the very end, we see that we have x to the 1st as our higher top exponent over 2. Since 1 is less than 2, this is saying that our horizontal asymptote is where y equals 0. So we know a little bit about the horizontal asymptotes. I think those are pretty easy. For the vertical asymptotes, let's see what's up with these. I think I already passed them. Let's see where they're at. Vertical asymptotes, pretty much finding the domain. So it's going to be the same kind of deal where how we were solving for the domain. In this case, x squared minus 9. We factor it, and then we just say that the lines for the vertical asymptotes are x equals that number that's excluded from the domain. So this is going to be pretty easy. So that was for horizontal asymptote. Now for vertical. If we solve this, 3 minus x, and this equals 0, eventually 3 is going to be equal to x. That's our vertical asymptote. So we got that. We do the same thing for x squared minus 1. You might notice a difference of squares, so you can say the following, that this is going to occur when x equals -1 and where x equals +1. So we actually have two vertical asymptotes here. So when this is graphed, the line will not hit here, and it won't hit when x is 1. So we've got these two. If we solve x squared minus 9, this is x plus 3, x minus 3 equals 0. We can say that in this case, we have two vertical asymptotes when x equals 3 and when x equals -3. Finally, for the last one, this might not have any. X squared plus 1 equals 0. This can't happen because, again, if you try to solve for x, you end up with x squared equals a negative number. Not happening. So there's actually no vertical asymptote. If you have any questions on these examples, please let me know. Come to class with them. Get familiar with the properties that I mentioned here. Domain and vertical asymptotes are very similar, so be on the lookout for those.